Hello, and welcome to today's statistics lesson. We're going to start talking about probability distributions. We are now talking about probability distributions, meaning we have moved from discrete probability distributions. We're going to move into continuous probability distributions. So you have seen some probability distributions before. We called them histograms at the beginning of this course. If I draw the histogram for the flipping a coin 4 times, the probability of getting 0 heads, 2 heads, flipping a coin twice, the probability of getting 0 heads, 1 head, or 2 heads. It's flipping a coin twice. So that's a coin flip twice. You drew that histogram because the probability of getting none was, there was a 1 out of 4 or a 0.25 chance. And here you had a 0.5 chance, and here you had a 0.25 chance, and this was a 1, and this was a 2, and this was a 3. Now, this is actually a probability distribution. I wanted to kind of take the mystery out of that. If you made the histogram for flipping a coin twice, the ways it could come up is tails, 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 heads. Whoops, sorry, the writing's a little delayed. Heads, tails, or heads, heads. So there were 4 possibilities. And if I said, how many times did you get 0 up until but not including the 1 heads, you would have said, oh, there were 1. How many times did you get 1 head? There were 2 of those. How many times did you get 2 heads? It was 1 of those. So 1 out of 4 was no heads. 1 out of 4 was 2 heads. And it really wouldn't be 2. You really probably would have put the 0 there, the 1 there, and the 2 there to represent how many. But this is a probability distribution for flipping a coin twice. And what we're going to see is the area under any probability distribution graph has to add up to 1, just like when we had a table. If we made a table out of this, which is how you started when we did a histogram, you made a table, the probability of getting no heads, and the probability, here's the probability, was 1 out of 4, or 0.25. And the probability of getting 1 head was, I'm sorry, you can't read that, 0.5. There's a little bit of a delay from when the pen does this to when I see it. And the probability of getting 2 heads was 0.25. And if you believe that the bottom and top numbers are 0.25, you add these up and you get a 1. The fact that we're showing you all these graphs of probabilities now confuse you. If I asked you what's the probability of getting 0 or 1 heads, you would add this area up and this area up. And I want to remind you that the area of a rectangle is length times width, or width times height, or the 2 dimensions multiplied together. Here, the dimension is a width of 1 for one more head, and the height here is 0.25. 1 times 0.25 is 0.25. Here you have another 1, and this is 0.5. 1 times 0.5 is 0.5. You would add them, and the probability of getting 0 or 1 head is 0.75. Or you could count them here again, but this is a graphical way of representing that. So then we start talking about another type of distribution, the standard normal distribution. You have heard this called the bell curve. The graph of the standard normal distribution is bell-shaped. Now, all normal distributions are bell-shaped. When we call it standard, what we mean is we've adjusted our numbers to make the mean 0 and the standard deviation 1. And this is going to bring us back to our idea of z-scores, 1 standard deviation below or 2 standard deviations below. We touched on that a little in the beginning of the course, but we're going to see that in a more detailed way here. So here we develop the skills to find areas or probabilities or relative frequencies corresponding to various regions under the graphs we're talking about. So let me put the pen back so this will let me control this. It's supposed to let me control this. Let's see. Whoops, sorry. There we go. So we're going to develop the skills to find areas of probabilities corresponding to numbers we're interested in under the graph of a standard normal distribution. And then we're going to talk about z-scores and where they correspond to areas under the graph. If you put a normal distribution in a standard form, then a z-score of -2 always means the same percentage as it does for any other normal distribution put in standard form. So first we're going to start with things that are not normal distributions, just give you this idea of area. But this fancy equation here, don't let that freak you out. It's in your calculator. We're not going to use it, but it is a normal distribution. And you can see it's an exponential function. There's a lot of exponential functions in the news around the time when there's a pandemic going on. This is an exponential function. This becomes a number on the bottom. This e is a number. You don't have to know this, but notice the things that are in there. There's your data point x. So your height at some value, one of your data points, you subtract the mean. This is how you are standardizing it and dividing it by the standard deviation. That's how you standardize the normal distribution. Instead of just doing e to the -1/2 x, you make this data point relative to how far it is from the mean and how many standard deviations that represents. Okay, so you're not going to have to use that funny looking graph. Don't let that make you nervous. Well, you're going to have to use the graph, but you're not going to have to plug into that equation. So this is what we mean by a bell-shaped graph. The mean is in the middle, okay? And out here would be a z-score of 1, a z-score of 2, and then out here would be a z-score of -1, a z-score of -2. One standard deviation away to the right is a z-score of 1. One standard deviation away to the left is a z-score of -1. We'll see that in a graph later on, probably in the next video. Now here's a different type of distribution, something we call a uniform distribution. So as long as it has an area of 1 under the curve, it can be a probability distribution. Uniform, everything is equally likely to occur. The area under the graph of a continuous probability distribution is always equal to 1. There's a correspondence between the area and the probability, so if we can find areas, we can find probabilities. And we can use rectangles for some of these more easier looking curves to find areas. So a continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. In other words, if no one, and we're going to talk about wait times, if no one wait time is any more likely than any other, then you'd have a uniform distribution. The density curve is the graph of the continuous probability distribution. It's called a density curve, and its area underneath has to be 1 in order for it to be a probability distribution. So because its area is 1, if we find what part of that area of 1 we have, we've found a probability. Waiting times for airport security. During certain time periods at JFK Airport in New York City, passengers arriving at the security checkpoint have wait times that are uniformly distributed between 0 and 5 minutes. So you might wait 0 minutes, you might walk right up, you might wait 5 minutes. And this distribution is illustrated in the next page. So all of the different possible waiting times are equally likely. You're just as equally to wait 1 minute or 1.357 minutes or 2 minutes or 2.5 minutes as you are any other up until 5. No possibility you're going to wait 6 minutes. No possibility your wait is negative. That, of course, makes sense. So this area is a 1. This goes from 0 to 5. So right minus left. 5 minus 0 is the width. And the height is 0.2. 5 times 0.2 is 1. That's where that comes from. So this is a valid probability density curve. So wait times, the reason this is continuous and not discrete is you don't wait just exactly a quarter of a minute or a half a minute. You could wait any amount of minutes in between 0 and 1 or 1 and 2. So it's possible to have a wait time of like 1.23, 4, 5, 6, 7 minutes. Or 1.23, 4, 5, 6, 7, 8, 9, 10 minutes. 9, 0, 1, 2, 4, 5 minutes. You could, any amount, it's a continuous, think of an analog watch with a sweeping hand. It could be anywhere there. It's not just you either waited a half a minute or a quarter of a minute. So this is continuous. So the enclosed area is exactly 1. We said that in general, the height of the vertical line in the uniform distribution is just 1 divided by the range. So if you can go from 0 to 5, the height has to be 0.2 in order to make 0.2 times 5 be 1. So each of these probabilities is a possibility of 0.2. Now, given this uniform distribution, this is not very useful for finding the time, the likelihood, a probability that a passenger waits exactly 2 minutes. The answer to that would be 0, because exactly 2 minutes would be a vertical line. There's no width. What these are used for are finding things like at least 2 minutes or more than 2 minutes, or a range of intervals of your variable. So find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. It might be helpful to draw the area we're looking for there. I don't think I picked up the pen yet. Okay, now I've got the pen. So here's the 2 minutes. So pretend that goes straight up and down. Really what they're asking us, at least 2 minutes, means 2 or more minutes. The word at least means that number or more. So I want to know, I want to shade it like this. I want this whole area here. And it's not shading very well, but you get the idea. So I'm going to go, the width I'm interested in is 5 minus 2. You do right minus left. 5 minus 2 is 3. And the height is 0.2. If I do 3 times 0.2, sorry, this is not letting me see what I'm writing, I will get 0.6. It's not going to give me that 6, is it? 6. I have to go a little slower. So at least 2 minutes, the probability is 0.6. Less than 2 minutes, the probability will be 0.4. 2 times 0.2. That's what we use probability distributions for, is to find the probability of something, of having at least this many or at most this many, and not just a single variable, because that will always be a 0 if it's a continuous variable, continuous random variable. So let me put the pen away. Put the pen away. Good. And put the pen away? No. Put the pen away. There we go. And now this should let me do this. Okay. It's just there's a little delay going on here, and I'm not sure what that's about. And that's bothering me. Okay. Whoa, now it goes crazy. Yes. All right, that's the example I just did. And now it's moving on. Hang on. Okay, and here's a nicer drawing of what I tried to show you. If you wanted to know the probability of waiting at least 2 minutes, it means 2 or more. So you would shade everything up to the highest point and then find the area of this. Now this is easy because it's a rectangle. You might not always have rectangles. You might want to keep in mind that the area of a triangle would be 1/2 times the base times the height. If this curve came down like this instead of going straight over, it would not be a uniform distribution anymore. But you can find probabilities from areas if you have probability density functions. Okay, in the next video, we're going to talk about the normal distribution specifically. So that's all I have for now. And email me if you have questions.